Hello everybody. In this lesson we're going to take a look at right triangles and a special relationship their sides have in the Pythagorean theorem. And we'll also go through a little bit of the background behind it and talk a little bit about Pythagoras of Samos. So first let's talk real quick about right triangles, right? What's the distinct defining characteristic of a right triangle? Hopefully you just said the right angle, right? Of course that's what makes a right triangle, right? We've got a right triangle here, a right angle in the corner, and the side that's opposite that is always the longest side, called the hypotenuse, right? This happens because the larger I make an angle, the larger the side across from that angle turns out to be. And in a right triangle, you've got a right angle which is 90 degrees. These other two angles have to be less than 90. And therefore the sides opposite those have to be smaller than this side, which we call the hypotenuse, our largest side. So the Pythagorean theorem, most of you probably know the Pythagorean theorem. I'm sure most of you have probably heard it before or maybe used it in your previous classes. And here's the Pythagorean theorem. It says that for any right triangle, when my two legs are A and B, and we call those two sides legs, there's no real distinction between which is the shorter side, which is the medium side. It doesn't really matter. For all intents and purposes, they are not the longest side, and that's really all we care about. The Pythagorean theorem states that in any right triangle, the squares of the lengths of the legs, a squared plus b squared, will equal the square of the third side, the square of our hypotenuse. So if a and b are our legs, c is our hypotenuse, then we know that a squared plus b squared will have to equal c squared. That's Pythagorean theorem. Okay? But what I want to talk real quick about is I want to take a little sidebar and talk about Pythagoras of Samos. This is the man that the theorem is named after. But what's interesting is that the theorem wasn't really something that Pythagoras came up with, nor were his followers and he the first people to use that relationship. Pythagoras was a Greek philosopher and a mathematician as well, and did a lot of traveling. He lived around 500 BC, and like most ancient civilizations, the society in which he lived was primarily agricultural. Remember that we're talking 500 BC here. That's about 2,500 years ago. Most people worked hard labor all day long, and for the most part, few people sort of concerned themselves with exploring the world around them. Pythagoras, however, was fascinated by the things that he saw around him as he traveled, and in particular, had a strong passion for mathematics and music. There wasn't really education back then. There weren't really schools that people went to like we have today. Most of the people just sort of worked in the fields and went about their daily chores, went about their daily jobs, and weren't really concerned too much with anything else. There were some people around him, however, that shared his fascination and his curiosity and sort of the way things worked. And he developed a bit of a following. And he and these followers formed their own little group where they could kind of get together and learn from each other's findings. And of course, learn about the wisdom passed on from their leader Pythagoras. And this would be sort of one of almost the first examples of a school-like setting that we can kind of think of and find. They didn't really get together in a building or anything, but they would get together and, as I said, they would kind of share their ideas. And these followers, since Pythagoras was their leader, they called themselves the Pythagoreans. And mathematics is one of the primary areas that they studied, although they studied tons and tons of different things, from art to music to science, things like that. But the Pythagoreans saw the power of this relationship between the legs and the hypotenuse of the right triangle, and there were lots and lots of different places where they could use it. And so they used it quite frequently. And historians have found that this relationship has been known long before this society existed. They actually have found Babylonian stone tablets that date back to around 1000 BC that have some examples of these. So I reveal these here. And we also know that the Egyptians also knew about this relationship. In particular, the Egyptians would use knotted rope. They didn't really have rulers or anything, so they kind of knotted ropes at equal distances, and that's how they would measure most things. And they discovered that they could make a very nice 3-4-5 triangle, which 3-4-5 satisfy the Pythagorean theorem. And so they've used those kinds of relationships, and there were a lot of things that they did that used that relationship. And so we know it was known before Pythagoras and his followers. But Pythagoras and his followers were the first people that were able to mathematically prove that it worked for any right triangle, regardless of the values of the sides. As long as you had a right triangle, they could prove that a squared plus b squared would always equal c squared. And so they were the first people to prove it and the first people to put it in print. And so they sort of dedicated it to their leader, Pythagoras, and named it the Pythagorean Theorem. And that's kind of where that sort of came from. Okay? So, Pythagorean Theorem, a squared plus b squared equals c squared. Why do we care about Pythagorean Theorem? Why do we want to use it? Well, the nice thing about Pythagorean Theorem is it allows us to, when given a right triangle, if we have two of the sides, we can guarantee to find the third, regardless of which side we're looking for. If we're missing a leg, we can find it. If we're missing a hypotenuse, we can find it, as long as we have those two other sides. So let's take a look at a couple examples, and we'll go through them. What I'd like you to do is, as we go through these examples, this is a video, so you can pause it at any time, right? What I'd like you to do is pause it when we start a problem, and I want you to try the problem on your own first. Maybe take a minute or two, see what you can get. If you get stuck with it, certainly hit play and then kind of work through it with me. But try it on your own first, okay? So here we go. We're going to the next page. First problem I want to take a look at. Carrie wants to walk to her friend Stacy's house. If she decides to cut through the park to save time, how much less distance will she have to travel? So we got Carrie's house, and we've got Stacy's house. Those are the houses shown here. Here's Carrie's house. Here's Stacy's house. I know she can get to Stacy's house by walking up the road, going for 3 blocks, and then going over 4 blocks on this other street. And we know she can do that. But that's a lot longer than cutting through the park. And the park, we've got this nice little diagonal distance here. And these 3 sides make up a right triangle, which means that we can use our handy-dandy Pythagorean theorem, which we love. So, Pythagorean theorem, a squared plus b squared equals c squared. And all we're doing is we're going to plug in some values. We want to figure out how far she would have to walk through the park. And then we can answer the question of how much less distance she'll have to travel if going that path. So, we've got our right triangle, right? If you look at sides 3 blocks and 4 blocks, those are both the legs, right? Because this one opposite here, this is the hypotenuse, okay? So we don't need to worry about that one for right now. For now, that's going to be side C. We always call the hypotenuse C. And the other two are A and B. It doesn't matter which one we call which. I'm going to call A the 3 block one. I'm going to call B the 4 block one, but it's totally up to you. You can switch those if you want. So now we're just going to plug those each in, right? So 3 blocks goes in for A. So this is going to be 3 squared plus 4 blocks goes in for B. So I've got 4 squared there. And C squared, this is the distance we're looking for. That's the distance through the park. And we go ahead and solve for C. So 3 squared gives us 9. 4 squared gives us 16 equals C squared. We're almost there. 9 plus 16 gives us 25, right? And now the last thing I have to do to solve for C, since I have C squared, I want to get C. What would undo squaring? Well, the opposite of squaring is square rooting, as we've been talking about the last few days, right? So that's what we're going to do. We're going to square root both sides, and that will give us C. Now, normally, we always say we need to make sure to remember that it could be plus or minus, right? When we square root both sides, it could be positive or negative. But in this case, since we're talking about a distance through the park, we don't really need to worry about the negative one. So square root of 25 will give us 5. So I have C equals 5. That means that the distance through the park, this would be 5 blocks. And we're done! Woohoo! Wait, no, we're not quite done yet. We haven't answered the question, right? We found the distance through the park, but the question does ask how much less distance will she have to travel. Well, of course, that's pretty easy to figure out. We know that she walks 3 blocks up this way, she walks 4 blocks over this way, and by the time she finishes, she would have walked 7 blocks. So to compare these two and answer the question of how much less distance, well, it's 5 blocks through the park, therefore 7 minus 5 gives us 2 blocks less. And that's going to be our answer. Okay, that's what we're looking for that. So good application of our Pythagorean theorem. Good so far? Questions? I don't see any hands up, so I'm going to assume that we don't have any questions. And we'll move on to the next problem. All right, so in this next problem, we've got a ladder resting against a house. The ladder is 20 feet long, we can see right here. Here's our ladder. And it is placed 10 feet from the wall, so I know this distance here is 10 feet. We want to know how high on the wall it reaches. All right, so now's the time to pause it and try it on your own first. And hopefully by now you've tried it on your own. If not, pause it. I told you to pause it. Listen to me. Okay, now I'm going to assume that you have paused it and unpaused it now and are ready to go through it. So let's take a look. Again, we're going to use Pythagorean theorem, right? We've got a right triangle. We've got a little right angle down here where the distance here meets the height on the wall. But this time I'm not looking for the hypotenuse, right? This time we have it. It's 20. This time I'm looking for one of the legs. And again, doesn't matter what you call each one. I'm going to call the question mark B. And I'm going to call this 10-foot side A, And of course, our hypotenuse always has to be called what? Always has to be called c. So now I'm going to plug these values into our Pythagorean theorem. So we have a squared, that's 10 squared, plus b squared. Well, we don't know what b is, so for now it's going to be b squared. And that's going to equal our hypotenuse squared, which is 20 squared. And now we're going to go ahead and compute this. So 10 squared, that's nice and easy. We've got 100. Plus b squared equals 20 squared. That's not too bad. That's going to be 400. And at this point, we're going to try to solve for b, right? Now, if I'm solving for b, what I want to do is get rid of the 100. I have here 100 plus b squared. I want to get that 100 out of there so I can get b squared by itself. So we subtract 100 from both sides. Minus 100, minus 100. I get b squared equals 300. And now I'm going to square root both sides because I want b alone. Right now I have b squared, so to undo that, b squared. Square root both sides. I get b equals, and now we turn to our handy-dandy calculator. Let me get my calculator out here. And we're going to do the square root of 300, and we should get, to the nearest tenth, we get 17.3. Our decimal goes 0.320508, blah, 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 blah. So the nearest tenth is 17.3. And this is in feet. We should always, of course, put our labels on. Look good so far? Okay. Hopefully you've been following so far. We got one more to do. One more down. Go to the next page here. In this next example, we have a square. Very little information. We're given the area is 40 inches squared, right? And we want to find the length of the diagonal. Okay, we've got a square. And if we take a look, this diagonal splits it into two right triangles, right? Excellent. All right, so go ahead and pause it. Try the problem if you can. All right, I'm going to assume you've tried it. Am I assuming correctly? I hope so. Okay, so assuming you've tried it, let's take a look. Now, to find the diagonal, I'm going to need to know the lengths of these two sides. If I know these two sides, then I'll be able to plug in the Pythagorean theorem to find the hypotenuse. I don't know the sides right now, but I do know the area, correct? And if I have a side of a right triangle, I'm going to call this side A. What do I do with that side to get the area? I square it, right? If I square the side length of the square, I get the area. So I know a squared must equal 40 square inches. Okay? So I'm going to take that and I'm going to do the square root of both sides. And that should give me my side length. Again, normally plus or minus square root, but in this case I'm looking at a length, so I don't need to worry about positive. And of course we get to our handy-dandy calculators. We do the square root of 40, and we get 6.3. And again, it's 0.32455, blah, 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 blah. So nearest 10 is 6.3. And this is in inches. That means that A is 6.3. And likewise, this is 6.3 up here. And now I can use those two to find the hypotenuse. This side up here is basically our B value. These are our two legs, our 6.3 and 6.3. Now we can plug in Pythagorean theorem. A squared plus B squared equals C squared. So A was 6.3. B was 6.3. And we square both of those. Now we could certainly take a look up here and realize that A squared was actually what we had before. So what would be best is probably putting in 40. But we'll do this kind of both ways. We'll assume this is 6.3, and we'll multiply by 6.3. And here we get 39.7 to the nearest 10. Plus 39.7 equals C squared. We can add these two things together. 39.7 plus 39.7. We get 79.4 equals C squared. And of course, to solve for C, we square root both sides. So square root of C, square root over here. 79.4, if we do the square root of that, we should get 8.9 to the nearest 10. And that should give us C. So this is 8.9. And again, our unit is in inches. Hopefully we were able to follow that relatively well. And I hope that made a little bit of sense. All right. I'm going to sign off right now. Enjoy the rest of your weekend.